Hello everyone, I'm Suchita More. Welcome you all in the video lecture on the topic Properties of Z Transform Part 3. In Part 1 and Part 2, we discussed the properties of Z Transform, that means definition of Z Transform, then linearity property, change of scale property, and multiplication by n property and examples on this. Our next property, if Z transform of f of n equal to capital F of Z, then Z transform of f of n upon n plus k, its value equal to this. For this proof, we consider left hand side of the proof. Then apply definition of Z transform. Here f of n upon n plus k. Here Z to the power minus n in terms of summation. Now we adjust the Z to the power k and here Z to the power minus k term. Now here we write down this j to the power k here, summation as it is, f of n as it is, and this j to the power minus n plus k and n plus 1 in terms of integration. Integration of this term, this complete term is equal to this. Therefore, we write down integration j to infinity, j to the power minus n plus k minus of 1. Then we write down the step as j to the power k, integration j to infinity, then summation f of n value, then j to the power minus n, and this k, j to the power k and this minus k we adjust in the denominator, and this is this value, summation value is nothing but this is the summation value f of n j to the power minus n is nothing but the capital F of z value, and hence proved. Now, problem on this, find the Z transform of 1 upon n plus 1. We apply the previous property. This is the property. Now, in this property, here value of k equal to 1 and f of n equal to 1. Therefore, here z as it is to the power 1, integration from z to infinity f of z. Now, whenever value of f of n equal to 1, then capital F of z, that means the transform of 1 is z upon z minus of 1. Therefore, we substitute this value here, 1 upon z to the power 1 plus 1, that means z square. This 1 z get cancelled, we get this value. Integrate this for, we adjust the term, or we solve this by partial fraction. If we solve this by partial fraction, then we get the value of a equal to 1 and b value equal to minus 1. And then solve the integration. Here log of z minus 1 first term, integration of this term, and integration of 1 by z is log of z, limits from z to infinity. Now whenever the values are z to infinity, we directly write down the answer as minus z log of z minus 1 upon z. But if we simplify this here, z as it is log of z minus 1 upon z, this is the term. We taking here, if we substitute the upper limit and lower limit, we get infinity by infinity form. Therefore, we taking this z common from numerator and denominator term, and this cancel the terms and then substitute the limits. Then we get here this term is z into log of 1 minus 1 by z, and after simplification we get same value. Here minus of this term. Therefore, the value of this z transform of 1 upon n plus 1 equal to this value. Now, shifting theorem is shifting fn to the left. Now, for this z transform of f of n plus k equal to z to the power k into f of z minus summation I equal to 0 to k minus 1 f of I z to the power minus I, where k is greater than 0. Now for this we consider the left hand side of the proof, that means z transform of f of n plus k. Apply the definition here, then adjust the z to the power k here, then we substitute n plus k equal to m. Therefore, we find out the limit for this n equal to 0, then m equal to k. in terms of summation here, and secondly upper limit is here infinity, therefore n equal to infinity, m tends to infinity. Now therefore equation 1 implies z transform of f of n plus k equal to z to the power k as it is in terms of summation m equal to 0, therefore m equal to k f of m z to the power minus m. This gives the equation number 2. Now we consider this in summation m equal to 0 to infinity f of m z to the power minus m. Here we break the terms, summation terms from m equal to 0 to k minus 1 and k to infinity, and then multiply both sides by z to the power k. Then we get here z to the power k term, here z to the power k, and z to the power k term. Now we know that this is the definition of z transform, and this value equal to capital F of z. And then second term as it is. Now z to the power k into this summation value, summation from k to infinity, its value by equation 1 is f of z transform of f of n plus k. Now we shifted this term on other side, and then taking z to the power k common, f of z minus of this term, and this m is replaced by I because the last answer or property in terms of I, therefore m is replaced by I, and we get the required result. Now by using this previous property, find out the z transform of 1 upon n factorial and z transform of 1 upon n plus 1 factorial. Now 1 upon n factorial z transform is summation n equal to 0 to infinity 1 upon n factorial z to the power minus, and this is the definition of z transform. Now we substitute m equal to 0, then we get this value, n equal to 1 we get second term, n equal to 2 we get third term. In this way we get the terms. Now this is the z to the power minus 1 means 1 by z to the power minus 2 means 1 by z whole square. In this way we write down the series. Now we know that expansion of e to the power x is 1 plus x square by 2 factorial and so on. Observe this series. Then here instead of x here 1 by z. Therefore z transform of 1 upon n factorial, its value is e to the power 1 by z, or z inverse of e to the power 1 by z equal to 1 upon n factorial. Now by applying shifting theorem, we find out the value of z transform of 1 upon n plus 1 factorial. Now here this is the property. Here substitute the value of k equal to 1 here. Therefore z to the power 1 f of z. Now here k minus of 1, that means 0 to 0, therefore we get f of 0 value only. And we know that f of 0, its value equal to 1. Therefore f of 0, that means f of n equal to 1 upon n factorial, its value 1. Therefore we get this is the result. In this way we solve the problems by using the shifting theorem. Now shifting with discrete unit step function, and here shifting fn to the right. Here z transform of f of n equal to capital F of z, and here this value z transform of f of n minus k u of n minus k equal to z to the power minus k f of z, or in terms of inverse. Here we consider g of n equal to this bracket value equal to f of n minus k u of n minus k. We know that by the definition of unit step function and display unit step function, its value is n is less than k, its value equal to 0. When n greater or equal to k, its value f of n minus k. We use equation 1. By definition of z transform, here z transform of g of n equal to this value. In next step, we summation n equal to 0 to infinity divided into two parts, 0 to k minus 1 and k to infinity. For first value, g of n equal to 0. For second term, its value equal to f of n minus k by using 1. Then here we adjust j to the power minus k term and here k term, and substitute n minus k equal to m, where when n equal to k, find out value of m equal to 0. N tends to infinity, m tends to infinity. We substitute here these values, then we get summation m equal to 0 to infinity f of m j to the power minus m. Here j to the power k as it is, this value equal to capital F of j. And we got this result in terms of z inverse. We write down this. Now by using this property, find out z inverse of 1 upon z minus of a. This is the property. Now here we adjust this z term. Here the z and this z. Multiply and divide by z. Then z to the power minus 1 into z upon z minus 1. Now here k equal to 1. F of z equal to z upon z minus of 1. Fn equal to z inverse of this, that means a to the power n. Therefore, f of n minus 1, its value is f of n equal to a to the power n, then f of n minus 1 equal to a to the power n minus 1. We substitute this value here and which is the required result. Similarly, we can prove the z inverse of these terms. These are the standard result. If we write down this z inverse in the form of intervals, n is greater or equal to 1 because k value is 1, its value is a to the power n minus 1, and if n is less than 1, its value equal. In this way, we solve the problems by using the properties of Z transform. Thank you.